Today we'll discuss the curious case of the history of L'Hopital's rule. Hospital's rule, or better in French, L'Hopital or L'Hospital rule, is used extensively in calculus to evaluate limits of the indeterminate forms 0 upon 0 and infinity upon infinity. The rule was first published by the French mathematician Guillaume de Hospital in 1696 in a book whose title can be roughly translated to English as Analysis of the Infinitely Small for the Understanding of Curved Lines. Now, this book is considered to be the very first book on differential calculus. It is somewhat controversially believed that the rule, which goes by the name of L'Hopital, was introduced to him in 1694 by his teacher Johann Bernoulli. Hospital met Bernoulli at the end of 1691 when Bernoulli was just 24 and was new to the mathematics world. By then, L'Hopital was already a member of important circle consisting of mathematicians and physicists. L'Hopital identified the talent of Bernoulli and employed him to give him private lessons for a short period of time. There have been historical accounts which indicate that L'Hopital may have paid Bernoulli a retainer in lieu of his discoveries and may have signed a pact that Bernoulli would hide his discovery from others. Initially content with the agreement and the princely sum, Bernoulli continued to honor their agreement. It was when the accolades bestowed on L'Hopital's work, he grew increasingly unhappy. Bernoulli complained that he had not received enough credit for his contributions, in spite of the preface of L'Hopital's book, which says, "I recognize I owe much to the insights of Bernoulli, especially to those of young John, currently a professor. I did unceremoniously use their discoveries as well as those of Mr. Leibniz. For this reason, I consent that they claim as much credit as they please and will content myself with what they will agree to leave me." It was in 1704 when L'Hopital died, Bernoulli publicly revealed of their agreement and claimed credit for almost everything of real interest in L'Hopital's book. At that time, barring Leibniz and few others, everyone in France regarded his claims as ridiculous, primarily on two counts. One, L'Hopital's mathematical talent was well regarded, and two, Bernoulli was involved in several other priority disputes, including one with his brother and later in his life with his own son. However, it was in 1921, a manuscript of Bernoulli's lectures on differential calculus from 1691 to 1692 was discovered in the Basel University. The text showed remarkable similarities to L'Hopital's writing, substantiating Bernoulli's account of the book's origin. Considering all that, somewhat arguably, I can say that if history had played itself differently, we would have been discussing the Bernoulli's rule today. In this video, we'll discuss the necessary conditions required and the statement of L'Hopital's rule, and we'll also discuss with example when we can apply and when we cannot apply L'Hopital's rule in a given limit. Now, for L'Hopital's rule to hold, there are four conditions that are needed, and the first condition is these functions fx and gx, they have to be differentiable functions in an open interval I containing this point a, except possibly at x equal to a. Now, the second condition is this limit x tends to a, fx and gx, either it should be 0 or it should be plus or minus infinite. So, this rule holds when fx upon gx is either 0 upon 0 form or infinity upon infinity form with plus or minus sign. Now, the third condition is this g dash x, it should not be equal to 0 for all x except possibly at a. And the fourth condition is this limit x tends to a, f dash x upon g dash x, this limit, it must exist. And suppose this limit is equal to L. So if all the four conditions are met, then we can say this limit x tends to a, fx upon gx is equal to limit x tends to a, f dash x upon g dash x. Now we look at all the four conditions. Now the first condition is these functions fx and gx, they have to be differentiable functions except possibly at x equal to a. So let us take one example, which is limit x tends to 0, x into log mod x. Now if I'll put x as 0, so it'll be 0, and then log limit x tends to 0, log 0, it tends to minus infinite, so it is 0 into minus infinite form. Now I can write it as limit x tends to 0 log mod x upon 1 upon x, which is infinity upon infinity form. So now it satisfies the second condition, which is it is infinite upon infinite form. Now log mod x, this function, it is differentiable for all the values of x except x equal to 0, and 1 upon x, this is again not differentiable at 0. So here f and g, they are differentiable in open interval I except at x equal to a, for which we'll have to find this limit. So we can apply L'Hopital's rule at a point where fx and gx, they may not be differentiable. So now in this case, if I apply L'Hopital's rule, I can write limit x tends to 0 1 upon mod x. So I'll differentiate the numerator, and then derivative of mod x is mod x by x, and I'll differentiate the denominator, so it is minus 1 upon x square. So I can cancel mod x with mod x. I'll write limit x tends to 0 minus x, and which is 0. So in this case, the value of this limit is simply 0. So we may apply L'Hopital's rule even when the function f or g, or maybe both, they are not differentiable at x equal to a. Now to illustrate the second case, let us take up another example, which is limit x tends to 0 greatest linear function of x upon x. Now I'll try and solve this question, and beforehand I'm going to tell you I'm going to solve it in a wrong way. So when limit x tends to 0, so greater function of 0 is 0, x is 0, so it is 0 upon 0 form. Now this greatest linear function of x, it is not differentiable at 0, but we don't mind. So we'll take up any interval between minus 1 and plus 1, and we can still apply L'Hopital's rule. So if I'll apply L'Hopital's rule, I can write limit x tends to 0, then derivative of greatest linear function of x. Now when x is not an integer, greatest linear function of x, it behaves like a constant function, and derivative of constant function is simply 0, and derivative of x is 1, so the value of this limit is 0, which in this case is completely wrong. Now can you identify where did I go wrong? So what I can actually do is I can write this limit as limit x tends to 0 negative greatest linear function of x upon x, which is its left hand limit, and I can write its right hand limit, which is limit x tends to 0 positive greatest linear function of x upon x. Now when limit x tends to 0 negative, if I put x as 0 negative, so what is greatest linear function of 0 negative? So greatest linear function of 0 negative is minus 1, and here this value will be simply 0 negative. So minus 1 upon 0 negative is neither 0 upon 0 form nor infinity upon infinity form. This value is actually infinite. So for this left hand limit, I cannot apply L'Hopital's rule. Now on the right hand side, when x is 0 positive, greatest linear function of x is 0. X is also 0. Now here I have 0 upon 0 form. Here I can use L'Hopital's rule. So limit x tends to 0 positive. Now derivative of greatest linear function of x will be 0. X will be 1. So now this limit is 0. So limit x tends to 0 greatest linear function of x upon x, it doesn't exist, because on the left hand side I have infinite and on the right hand side I have 0. But if the question is limit x tends to 0 positive greatest linear function of x upon x, which is 0 upon 0 form, now we can apply L'Hopital's rule in this case to get this answer as 0. So second condition is L'Hopital's rule can only be applied if the limit is either of the form 0 upon 0 or plus minus infinity upon infinity. Now for this third condition, that is g dash x should not be 0 in this interval I except possibly at a. So I'll take up a counter example by mathematician Otto Stolz, and what he has done was he has taken two functions fx and gx. Fx is defined as x plus sin x into cos x, and gx as x plus sin x into cos x into e to the power sin x. And now we wish to calculate this limit, which is limit x tends to infinite fx upon gx. So if I write this limit, I can write this limit as limit x tends to infinite fx is x plus sin x into cos x, and here it is x plus sin x into cos x into e to the power sin x. Now I can cancel x plus sin x cos x. So I'll write this limit as limit x tends to infinite e to the power minus sin x. Now if I'll put this limit, I'll get it as e to the power minus sin infinite. And sin infinite, it is an oscillating value. So I'll get this result as an oscillating value which oscillates from e to the power minus 1 to e. So when I'm getting an oscillating result, in this case, we know that limit does not exist. Now I'll try and find f dash x. So if I write f dash x, so if I'll differentiate, I'll write 1 plus, I'll write it as sine 2x. So 1 by 2 sine 2x, so it'll be 1 by 2, and then derivative of sine 2x will be cos 2x into 2. So 2 and 2 will cancel. So I'll write 1 plus 2 cos square x minus 1. So I'll express this f dash x as 2 cos square x. Now I'll differentiate g dash x also. So if I'll differentiate g dash x, I'll write it as x plus sin x into cos x into derivative of this function, which is e to the power sin x into cos x plus e to the power sin x as it is into derivative of this function, which is again 2 cos square x. So now here I can take e to the power sin x and cos x common. So if I'll take e to the power sin x into cos x common, I can write it as x plus sin x into cos x plus 2 cos x. Now I'll find this limit, which is limit x tends to infinite f dash x upon g dash x. So limit x tends to infinite f dash x upon g dash x, this limit will be limit x tends to infinite f dash x is 2 cos square x, and then here it will be e to the power sin x into cos x, and here will be x plus sin x into cos x plus 2 cos x. Now if I put x is infinite, now it is oscillating value between 0 and 1. This is oscillating value between 1 upon e and e, oscillating value between minus 1 and plus 1, and then it is 1 upon infinite. So anything finite upon infinite will be 0. So in this case, limit x tends to infinite, f dash x upon g dash x will be 0. Now in this example, fx upon gx, it is infinity upon infinity form. As x tends to infinite, it will be infinite upon infinite. Functions fx and gx, they are differentiable functions. This limit x tends to infinite, f dash x upon g dash x, it exists and it is equal to 0. But still, this limit, it doesn't exist. So from his counter example, Otto is told, he mentioned that this condition g dash x unequal to 0 is required for L'Hospital rule to hold. Now if we look at g dash x, so if I'll put limit x tends to infinite, g dash x, so it will be oscillating value 1 upon e to e, and then this cos infinite, it changes, it oscillates between minus 1 and plus 1. So there are infinitely many points where this function g dash x, it is taking the value 0 in the neighborhood of infinite. And now the fourth necessary condition which is required for L'Hopital's rule to hold is this limit x tends to a, f dash x upon g dash x, this limit should exist. So for this, we'll take up an example, which is limit x tends to 0, x plus sin x upon x, which is infinity upon infinity form. So in this case, these two functions, they are differentiable and continuous. They are of the form infinity upon infinity, and then this x is unequal to 0 in this interval. Now, if I use L'Hopital's rule, I can write limit x tends to infinite. So if I differentiate the numerator, I'll get 1 plus cos x, and the value of x is 1. So if I'll put this limit, I'll get 1 plus cos infinite, which is an oscillating value, minus 1 to plus 1. So it is 1 plus oscillating value, minus 1 to plus 1. So I'm not getting an exact value, I'm getting an oscillating limit. So in this case, We'll say limit does not exist. But if I'll actually solve this question, I can write limit x tends to infinite. I'll cancel x with x. I'll write 1 plus sine of x upon x. So this is 1 plus, and then limit x tends to infinite sine x upon x. So it is 1 plus, and then oscillating value between -1 and +1 upon infinite. So anything finite upon infinite is nothing but 0. So actually this limit exists, and the value of this limit is 1. But using L'Hopital's rule, we are getting limit does not exist. So which gives us our fourth condition, and which is for this L'Hopital's rule to hold, this limit x tends to a f dash x upon g dash x, this limit should exist. Now there are numerous other examples where all the four conditions of L'Hopital's rule are met, but still if we use L'Hopital's rule, we'll go in the endless loop. Same is true with the second example also, which is infinity upon infinity form, differentiable also, and then denominator is not equal to 0. So if I'll differentiate, I'll write limit x tends to infinite 1 upon twice under root x square plus 1 into 2x. So which is limit x tends to infinite under root of x square plus 1 upon x, which again is infinity upon infinity form. So if I'll differentiate it again, I'll get limit x tends to infinite 1 upon twice under root x square plus 1 into 2x upon 1. So which is limit x tends to infinite x upon under root of x square plus 1, which again is infinity upon infinity form. So again, if we keep using L'Hopital's rule, we'll go in the same loop. And for this one, if I'll take x out, I'll cancel it. I'll get this limit as +1. So L'Hopital's rule, it may not be useful in all the cases. So the point is, L'Hopital's rule is an amazing rule, and students, they find it fascinating and simple, but then no one size fits all. So if studying L'Hopital's rule hampers you to study or give the equal importance to other ways to solve limits, then you need to reconsider, because there are many situations where L'Hopital's rule might not be useful, or it may not even be applicable. So now let us prove L'Hopital's rule. Now, as we already know, there are four conditions required for L'Hopital's rule to hold. And the first condition was the functions fx and gx, they have to be differentiable in the interval, except possibly at that point a, for which we want to calculate this limit. Second condition was this fx and gx, either both of them should be 0, or they should be of the form plus infinite or minus infinite. Now the third condition was this g dash x, it should not be 0 in the neighborhood of a. And the fourth requirement was this limit x tends to a, f dash x and g dash x, it exists, and this is equals to L. Now we'll consider a special case proof of L'Hopital's rule, and we are considering the case when fx and gx are continuously differentiable functions and limit x tends to a fx is 0 and limit x tends to a gx is 0. Now why are we discussing this special case proof? We are discussing this special case proof because at our level, when we deal with L'Hopital's rule, then we mostly deal with functions which are continuously differentiable. Say for example, polynomial functions, trigonometric functions, exponential function, logarithm function. All these functions, they are examples of continuously differentiable function. So let us get on with the proof. And the proof simply is, suppose I have to calculate this limit, which is limit x tends to a fx upon gx, and since fx is 0 and gx is 0, when limit x tends to a, so it is 0 upon 0 form. Now what I'll do is, I can write it as limit x tends to a fx minus fa upon gx minus ga, because the value of fa is 0 and the value of ga is also 0. So I can express limit x tends to a fx upon gx as limit x tends to a fx minus fa upon gx minus ga. Now what I'll also do is, I'll write it as limit x tends to a fx minus fa, and I'll divide it with x minus a, and I'll write this as gx minus ga upon x minus a. Now I'll take this limit in the numerator and denominator, so I'll write it as limit x tends to a fx minus fa upon x minus a divided by
limit x tends to a gx minus ga upon x minus a, and this limit fx minus fa upon x minus a, limit x tends to a is nothing but simply f dash a, and this limit gx minus g upon x minus a is g dash a. Now, because we have assumed that these functions fx and gx, they are continuously differentiable, now I can say this f dash a upon g dash a is actually equal to limit x tends to a f dash x upon g dash x, and that should be equals to L. So the condition that the function should be continuously differentiable is required because we want to express this f dash a upon g dash a as limit x tends to a f dash x upon g dash x. So from here we can say this limit x tends to a fx upon gx is equal to limit x tends to a f dash x upon g dash x in this special case when f and g, they are continuously differentiable, and limit x tends to a fx is 0, limit x tends to a gx is 0, g dash x is unequal to 0 in the neighborhood of a, and this limit x tends to a f dash x upon g dash x it exists and is equal to L. So that's our first case proof of fx and gx. Now we'll consider the case when limit x tends to a fx and gx, they tends to plus or minus infinite. Now let us take second case of L'Hopital's rule when this limit x tends to a fx and limit x tends to a gx, they tends to plus or minus infinite. So again, this proof is restrictive. We have made many assumptions. So in this case, the assumptions that we are making is these functions fx and gx, they are continuously differentiable. Limit x tends to a fx and gx, it tends to either plus infinite or minus infinite. G dash x, it is unequal to 0 in the neighborhood of a, and then limit x tends to a f dash x upon g dash x, it exists and it exists finitely, and suppose the value is L, and we'll also assume that this limit x tends to a fx and gx, it also exists finitely. So I'll start with limit x tends to a fx upon gx, and I'll say suppose the value of this limit is L1. Now we know that it is infinity upon infinity form. So I can write L1 as limit x tends to a 1 upon gx upon 1 upon fx. So 1 upon gx will be 0 and 1 upon fx will be 0. So I've expressed it as 0 upon 0 form. Now in the first case, we have already proved that this function or this limit x tends to a fx upon gx is equal to limit x tends to a f dash x and g dash x when it is 0 upon 0 form. So now in this case, I can apply L'Hopital's rule. So if I apply L'Hopital's rule, I can write L1 as limit x tends to a minus 1 upon g square x into g dash x minus 1 upon f square x into f dash x. So I can write it as limit x tends to a f square x upon g square x into g dash x upon f dash x. So I'll write it as limit x tends to a fx upon gx whole square, and then here I'll write it as 1 upon f dash x and g dash x. So now I'll separate the limits. So I'll write limit x tends to a fx upon gx whole square, and then limit x tends to a 1 upon f dash x and then g dash x. Now we know that limit x tends to a fx upon gx, it exists, and we have assumed that it exists finitely and its value is L1. So I can write this limit as L1, and that should be equals to L1 square and then 1 upon f dash x and g dash x. Now 1 upon f dash x and g dash x, so f dash x upon g dash x, this limit is equal to L. So I can write it as 1 upon L. So if I'll cancel L1 with L1, I can write L1 is equal to L. So by comparing these two values, I can say that limit x tends to a fx upon gx is equal to limit x tends to a f dash x upon g dash x when f tends to infinite and g tends to infinite. And in no way this proof is complete, because we have taken a very special case, and also we have made many assumptions that these limits, they exist and they exist finitely, and also that we can define L1 and L2 both separately. So with all these assumptions, we have proved this second case. So this proof in no way is general proof, and it doesn't claim that this proof holds for all the conditions for L'Hopital's rule.
Now here this first question is, if this limit x tends to infinite, eight x cubed plus mx square to the power 1 by 3 minus nx, it exists and is equal to 1, then the value of m by n is. What we'll do is, we'll let x as 1 by t, then this limit will be this limit t tends to 0 positive, and we can write this as 8 upon t cube plus m upon t square to the power 1 by 3 minus n upon t. Now if we simplify this, we can write this as limit t tends to 0 positive. This is 8 plus n t to the power 1 by 3 minus n divided by t, and this limit is equal to 1. Now, in order to solve this limit, first we'll check its form. If we put t as 0, we'll get this as 8 to the power 1 by 3, which is 2 minus n upon 0. Now, it has to be an indeterminate form to get this result 1. So that means from here we can say value of n must be 2. So if n is 2, then it is 0 upon 0 form. We can use L'Hopital's rule. We can write limit t tends to 0 positive, and it will be this 1 by 3 8 plus mt to the power minus 2 by 3 into m divided by 1, and it will be equal to 1. Now if we put t as 0, we'll get this as 1 by 3, and this is 8 to the power minus 2 by 3n, and it will be equal to 1. Now this is 1 by 12, so value of m is simply 12. Now once we have the value of m and n, the value of m by n will be equal to 12 divided by 2, which is 6, and that's your option B. Now here the question is, we need to solve this limit, which is limit x tends to 0 sine pi into cos square x upon x square. Now sine pi is 0, so this is 0 upon 0 form. We'll use L'Hopital's rule, so it will be this limit x tends to 0, and then it will be this cos pi cos square x, and then pi into 2 cos x, and then minus sin x whole divided by 2x. Now this 2 and 2 will cancel. Now sin x upon x, when x tends to 0, it is 1. Now when we put x as 0, this is cos pi is minus 1, and then we have this pi, cos 0 is 1, and then we have this minus 1. So answer to this limit is pi, and that's your option B. Now here the question is, we need to solve this limit x tends to 1 log 1 plus x minus log 2 3 into 4 to the power x minus 1 minus x upon, and this is 7 plus x to the power 1 by 3 minus 1 plus 3x to the power 1 by 2 sine x minus 1. Now what we'll do is, we'll use substitution here. We'll write let x equals 1 plus h. Then we can write this limit as limit h tends to 0 log 2 plus h
minus log 2, and here will be this 3 into 4 to the power h minus 1 minus h upon 8 plus h to the power 1 by 3 minus 4 plus 3h to the power 1 by 2, and here will be this sin h. Now we can write this as limit h tends to 0 log 1 plus h by 2, and we'll take sin h here, and we'll write 3 into 4 to the power h minus 1 minus h upon 8 plus h to the power 1 by 3 minus 4 plus 3h to the power 1 by 2. Now here what we'll do is we'll multiply and divide it with h. Now sin h upon h is 1, and here we'll also multiply and divide it with 2. So log 1 plus h by 2 upon h by 2, it will be 1. So now we are left with limit h tends to 0 3 by 2, and then it is 4 to the power h minus 1 minus h upon 8 plus h to the power 1 by 3 minus 4 plus 3h to the power 1 by 2. And we put h as 0, it is 0 upon 0 form. And once it is 0 upon 0 form, we use L'Hopital's rule. So it will be this limit h tends to 0, 3 by 2. Now this is 4 to the power h log 4 minus 1 upon, this is 1 by 3, 8 plus h to the power minus 2 by 3 minus 1 by 2, 4 plus 3h to the power minus 1 by 2 into 3. Now we'll put h as 0. Now if we put h as 0, we'll get this as 3 by 2 into log 4 minus 1, and here will be this 1 by 3, and then it will be 8 to the power minus 2 by 3, which is 1 by 4, and this is 4 to the power minus 1 by 2, so it will be this 3 by 4. Now we can write this as 3 by 2 log 4 by e, and here if we take LCM, it will be minus 8 by 12. Now this is 6, and this is minus 4 by 3. So this value will be minus 9 by 4 log 4 by e, and that is the answer to this limit. Now here the question is limit x tends to infinite x square sine log under root cos pi x. Now what we'll do is we'll let x as 1 by t, so it will be this limit t tends to 0 positive, and then it will be 1 minus t square sine, we'll take this power out, so it will be this 1 by 2 log cos pi t. Now if we put t as 0, now it will be this cos 0 is 1, log 1 is 0, so it will be this sine 0, which is 0 upon 0 form. Now we use L'Hopital's rules. We can write limit t tends to 0 positive. Now this is cos 1 by 2 log cos pi t into 1 by 2, and then 1 upon cos pi t, and then it will be this minus sin pi t into pi divided by 2t. Now we multiply and divide with pi also. Now this is cos 0 is 1. Now this also is cos 0, so it will be this one, and then sine pi t upon pi t, when t tends to 0, it is also 1. So value of this limit will be minus pi square upon 4. Now here the question is, let fx be a continuous odd function which vanishes exactly at one point. Now it is continuous odd function, and we know that for odd function f0 is 0 and f1 equals 1 by 2. That means this function, it will be in first and third quadrant with value at 0, 0, and at 1 this value is 1 by 2. Now we are given that capital Fx is this integral from minus 1 to x ft dt, and capital Gx is this integral from minus 1 to x t into mod of ft dt for all x belongs to minus 1 to 2. Now it is given that this limit x tends to 1 fx upon gx is 1 by 14. Now we'll write this as this limit x tends to 1 and then this integral from minus 1 to x ft dt upon this integral from minus 1 to x t into mod of f of ft dt, that is equal to 1 by 14. Now if we put x as 1, then limits of this integral will be from minus 1 to 1, and we know that fx is an odd function. So integral of an odd function from minus a to plus a will be simply 0. In the same way, this integral from minus 1 to 1 t into mod of f of ft dt. Now ft is odd, f of ft will be odd, but this mod sign, it makes an even function, and this t is odd, so this function is an odd function. So again, value of this integral will be 0. So this is 0 upon 0 form. Now if it is 0 upon 0 form, we can use L'Hopital's rule. So if we differentiate this, we can write this as this limit x tends to 1 fx, and here will be this x into mod of f of fx, that is equal to 1 by 14. Now if we put x as 1, we write this as f1 upon mod of f1, that is equal to 1 by 14. Now in the question it is given that value of f1 is 1 by 2. So it will be this 1 by 2 upon mod of f1 by 2 will be equal to 1 by 14, or mod of f1 by 2 is equal to 7. Now since fx is positive when x is greater than 0, so we can write f1 by 2 is actually plus 7. Value of f1 by 2 is 7, and that is the answer to this question. Now this second question is this limit x tends to 1 negative 1 plus cos inverse x to the power 1 minus x has the value which is the following. Now in this, what we'll do is we'll let x as cos theta. Now when x is 1, theta is 0. So from here we can say this theta tends to 0 positive. So we can write this limit as limit theta tends to 0 positive 1 plus theta to the power 1 minus cos theta. Now this is 1, and here it is 0 to the power 0 form. Now we can write this as 1 plus e to the power limit theta tends to 0 1 minus cos theta into log theta, and we can write 1 minus cos theta as 2 sine square theta by 2 into log theta, which we can also write as 1 plus e to the power limit theta tends to 0, and this is 2 log theta upon cosec square theta. Now this is infinity upon infinity form. So if we use L'Hopital's rule, we can write this as 1 plus e to the power limit theta tends to 0, and this is 2, 1 upon theta, and here it is this 2 cosec theta by 2, and then cosec theta is minus cosec theta by 2 and cot theta by 2, 1 by 2. Now we can write this as 1 plus e to the power limit theta tends to 0, and this is minus 2 sin theta by 2 sin square theta by 2 tan theta by 2 upon theta, and we multiply and divide it with 2. This is 1 and sin 0 is 0. So this is 1 plus e to the power 0, which is 1 plus 1, and that is 2. So answer to this limit is simply 2. And that's your option B. Now the question is, a function is defined from R to 0 to infinite, and gx be twice differentiable functions such that f dash and g double dash are continuous functions on R. Now it is given that suppose f dash 2 equals g2 equals 0 and f double dash 2 is unequal to 0 and g dash 2 is also unequal to 0. We need to find this limit, which is limit x tends to 2 fx into gx upon f dash x into g dash x, and it is equal to 1. Now first we'll check this form. Now it is f2 into g2, and g2 is 0 and f dash 2 is 0, so it is 0 upon 0 form, and when it is 0 upon 0 form, we'll use L'Hopital's rule. So we'll write limit x tends to 2. Now this is fx into g dash x plus gx into f dash x upon f dash x into g double dash x plus g dash x into f double dash x, and it is equal to 1. Now we'll put this limit. So we write f2 into g dash 2 plus g2 into f dash 2 upon f dash 2 g double dash 2 plus g dash 2 into f double dash 2, and it is equal to 1. Now we know that g2 is 0. So this expression will be 0, and also f dash 2 is 0. So it will also be 0. Now g dash 2 and g dash 2 will cancel. So we'll get f double dash 2 equals f2, and which is unequal to 0. Now in the question it says its codomain is from 0 to infinite. That means this f double dash 2, which is equal to f2, it is greater than 0. Now if we look at f dash 2, we know that f dash 2 is 0 and f double dash 2 is greater than 0. That means this 2 is a point of local minimum. So that means this option 8 is correct. That means this option B will be incorrect. And clearly f double dash 2 is equal to f2. That means this option C is also incorrect. Now it says fx minus f double dash x equals to 0 for at least one x belongs to R. We know that this is true for x equals 2. That means this option D is also correct. So the correct options are A and D. Now here the question is, it says if fx is a differentiable function such that f0 is 0, f pi by 2 is 3 and f dash 0 is 1, if gx is this integral from x to pi by 2 f dash t cosec t dt minus this integral from x to pi by 2 cot t cosec t into ft dt, then we need to find this limit x tends to 0 positive gx, since gx is only defined in the right neighborhood of 0. Now what we'll do is we'll solve this question taking cosec t as first function and f dash t as second function. So it will be cosec t and then integral of f dash t will be ft, and then limits are from x to pi by 2 minus this integral from x to pi by 2. Now derivative first, derivative of cosec t is minus cosec t cot t, and then integral of f dash t is ft dt, which will get cancelled with this other expression, which is the same integral from 0 to pi by 2 cot t cosec t ft dt. So this gx will be cosec pi by 2, which is 1, and then it will be this f pi by 2 minus fx upon sin x. Now f pi by 2 is 3, so value of gx is 3 minus fx upon sin x. Now we need to find this limit x tends to 0 positive gx. So if we take this limit x tends to 0 gx will be this 3 minus this limit x tends to 0 fx upon sin x. Now f0 is 0 and sin 0 is 0, so it is 0 upon 0 form. So we can use L'Hopital's rule. So it will be this 3 minus limit x tends to 0 f dash x upon cos x. Now this is 3 minus f dash 0 is 1 and cos 0 is also 1. So 3 minus 1 is 2. So answer to this limit is simply 2. Now here we are given that this function is defined from 0 to pi to r, and it is such that this limit t tends to x fx sin t minus ft sin x upon t minus x, it is equal to sin square x for all x belongs to 0 to pi. Now we put t as x, it will be 0 upon 0 form, and if it is 0 upon 0 form, we can use L'Hopital's rule. So we'll differentiate this numerator and denominator with respect to t. So it will be this fx and derivative of sin t is cos t minus f dash t into sin x upon 1, and this limit t tends to x, and it will be equal to this sin square x. Now we can write this as fx cos t minus f dash x sin x, and it will be equal to this sin square x. Now we can write this as f dash x minus fx cot x, and it will be equal to minus sin x, which is a linear function in y. Now we will find its integrating factor. Its integrating factor will be e to the power minus integral of cot x dx, and will be e to the power minus log sin x, which is nothing but cosec x. So we solve this integral, we'll get fx into cosec x will be equal to this integral and minus sin x into cosec x. So it will be this minus 1 dx, which is minus x plus c. So we can write this function fx as minus x sin x plus c sin x. Now we are given that f pi by 6 is minus pi by 12. So if we put x as pi by 6, f pi by 6 is minus pi by 12, and here will be this minus pi by 6, and sin pi by 6 is 1 by 2 plus c into 1 by 2. I'll cancel, value of c is 0. So from here we'll get this function fx as simply minus x sin x. So in our case, this function fx is minus x sin x. Now we have to find which of the following options is or are correct. Now this first one is f pi by 4. Now f pi by 4 is minus pi by 4 and sin pi by 4 is 1 by root 2. So it will be minus pi upon 4 root 2. Option A is incorrect. Now B is fx is less than equal to x to the power 4 upon 6 minus x square. Now we know that fx is minus x sin x and sin x is x minus x cube upon 6 plus x to the power 5 upon factorial 5. Now this is minus x square plus x to the power 4 upon 6 minus x to the power 6 upon factorial 5. Now it is this expression minus some value. That means it is always less than minus x square plus x to the power 4 by 6. That means this option B is correct. The actual way to solve this question is to prove first that this is true when x belongs to 0 to 1, and second it is true for x belongs to 1 to infinite. But this part is fairly simple. So we'll take this option B. Now in C it says there exists alpha belongs to 0 to pi such that f dash alpha is 0. Now for C we know that f0 is 0, f pi is 0, and this function is continuous and differentiable. Then using Rolle's theorem, we know that there is at least one alpha in the interval 0 to pi such that f dash alpha is 0. So that means this option C is also correct. Now option D is we need to find f double dash pi by 2 plus f pi by 2. Now f pi by 2, it is minus pi by 2. If we differentiate this, f dash x will be minus x cos x minus sin x. And if we differentiate this again, f double dash x will be minus x and minus minus plus will be this sin x minus cos x and will be this minus cos x. So f double dash pi by 2 will be this plus pi by 2 and cos 90 is 0. Now if we add them, plus pi by 2 and minus pi by 2, they will cancel. So this value will be 0. So the correct options are B, C and D. Now here we are given a recursive relation which is Pn, and it is A Pn minus 1 and let P1 be a to the power x minus 1. Now if we find Pn at 0, then it will be P1 0 is a to the power 0 minus 1, 0. And if we put P1 as 0, then P2 will be a to the power 0 minus 1, 0. So that's how we'll get all these P1, P2, Pn as 0. So Pn 0 will be 0. So you have to find this limit. X tends to 0. Pn upon x will be 0 upon 0 form. And if it is 0 upon 0 form, we can use L'Hopital's rule. So it will be equal to d by dx of Pn upon 1. Now we differentiate Pn, it will be this limit x tends to 0. Now this is a Pn minus 1 log a into derivative of Pn minus 1, and derivative of Pn minus 1 will be a P n minus 2 log a, and will continue up to this last one which is a to the power x into log a. Now if we put x as 0, we know that all P1, P2, Pn, they are 0. So a to the power 0 is 1. So value of this limit will be log of a to the power n, and that is the answer to this question. Now here the question is, we need to solve this limit x tends to 0 sine square pi upon 2 minus ax into secant square pi upon 2 minus bx. Now first we'll check its form. If we put x as 0, sine pi by 2 and sine pi by 2 is 1, and secant pi by 2 is infinite, so it is 1 to the power infinite form. we'll directly use the shortcut. So it'll be this limit x tends to 0, and then it'll be this secant square pi upon 2 minus bx into sine square pi upon 2 minus ax minus 1. Now sine square theta minus 1 is minus cos square theta, and we let the secant in terms of cos as well. So it'll be this e to the power minus, and then this limit x tends to 0 cos square pi upon 2 minus ax upon cos square pi upon 2 minus bx. Now x square, it is a continuous function, so we can take this limit inside. So we can write this e to the power minus, and then this limit x tends to 0 cos pi upon 2 minus ax upon cos pi upon 2 minus bx whole square. Now if we look at this limit, this is cos pi by 2, which is 0, and denominator also it is cos pi by 2, so it will again be 0, so it is 0.0 form. Now we can use L'Hopital's rule. Now if we use L'Hopital's rule, we can write e to the power minus, and then it will be this limit x tends to 0. Now differentiation of cos is minus sine, so it will be this minus sine pi upon 2 minus ax, and then it will be this minus pi upon 2 minus ax whole square into minus a, and the denominator will be minus sine pi upon 2 minus bx, and then minus pi upon 2 minus bx whole square, and then it will be this minus b whole square. Now if we put this limit, sine pi by 2 is 1. Now minus pi and minus pi will cancel. This minus and minus will also cancel. Now if we put x as 0, this will be this 4, which will cancel. So answer to this limit will be simply e to the power minus a square upon b square. Now here the question is, we need to solve this limit x tends to a 1 upon a square minus x square whole square, and then we have a square plus x square upon ax minus 2 sine a pi by 2 into sine pi x by 2. Now if we put x as a, it will be this 0 in the denominator, and the numerator will be this 2 minus 2 0, so it is 0 upon 0 form. Now what we'll do is, we'll subtract 2 and we'll add 2. Now we can write this as limit x tends to a 1 upon a square minus x square whole square, and here it will be a square plus x square minus 2ax, which we can write a minus x whole square upon ax, and then plus, we'll take this 2 common, it will be 1 minus sine a pi by 2 into sine pi by 2x. Now we'll multiply this a square minus x square whole square. So we can write this as this limit x tends to a, and it will be this a minus x whole square, and here will be this ax into, and we'll write this as a plus x whole square into a minus x whole square, and here it will be this 2 into 1 minus sine a pi by 2 into sine pi by 2x upon a minus x square into a plus x square. Now here a minus x whole square will cancel. Now we put x as a, we'll get this as a square plus 2a square. So there will be 1 upon 4 a to the power 4 and plus, now here we don't have a problem with this a plus x. So it will be this 2a whole square. So it will be 4a square. We'll cancel this 2 with 4. So we can write this as 1 by 2 a square into this limit x tends to a 1 minus sine a pi by 2 into sine pi x by 2 upon a minus x whole square. It will be sine a pi by 2 whole square, and a is an odd integer. So it will be 1 minus 1 0. So it will be 0 upon 0 form. So now we can use L'Hopital's rule. Now if we use L'Hopital's rule, we can write 1 upon 4a to the power 4 plus 1 upon 2a square limit x tends to a, and this is minus sine a pi by 2, and this is cos pi by 2x into pi by 2 upon 2 into a minus x into minus 1. Now this minus and minus will cancel. Now this again is 0 upon 0 form, because cos odd multiple of pi by 2 is 0 and a minus a is also 0. So we now get this as 1 upon 4a to the power 4 plus 1 upon 2a square, and then this limit x tends to a sine a pi by 2. Now this is minus sine pi by 2x, and then it will be this pi by 2 square divided by 2 into minus 1. This minus and minus will cancel. Now we'll put x as a. If we put x as a, we'll get this as 1 upon 4a to the power 4 plus 1 upon 2a square, and here will be this sine a pi by 2 into sine a pi by 2, which is 1 into, now this is pi square by 4, and we have this 2 here. So it will be this 1 upon 4 a to the power 4 plus pi square by 16a square. So we'll take this LCM. So it will be this 16a to the power 4, and then it will be 4 plus pi square into a square. And that is the answer to this limit. Now here the question is, we are given this function fx as log x square plus e to the power x upon log x to the power 4 plus e to the power 2x. Now if this limit x tends to infinite, fx is L, and x tends to minus infinite, fx is M, then find the relationship between L and M. Now for L, it will be this limit x tends to infinite log x square plus e to the power x upon log x to the power 4 plus e to the power 2x, which is infinity upon infinity form. We'll use L'Hopital's rule. So it will be this limit x tends to infinite, and then we can write this as 1 upon x square plus e to the power x into 2x plus e to the power x, and here it will be 1 upon x to the power 4 plus e to the power 2x into 4x cube plus 2 e to the power 2x. Now we can write this as limit x tends to infinite 2x plus e to the power x upon x square plus e to the power x into x to the power 4 plus e to the power 2x upon 4x cube plus, and this is 2 e to the power 2x. Now here we'll divide everything with e to the power x, and here we'll divide everything with e to the power 2x. So we can write this as limit x tends to infinite 2 x upon e to the power x plus 1 x square upon e to the power x plus 1, and here it will be x to the power 4 upon e to the power 2x plus 1, and this is 4 x cube upon e to the power 2x plus 2. Now we know the standard result that this limit x tends to infinite, x to the power n upon e to the power x, it is 0. And it is very easy to prove. This is infinity upon infinity form. So we'll keep using L'Hopital's rule. It will always be infinity upon infinity form. So if we differentiate this n times, we'll get this as factorial n upon e to the power x. Now this is factorial n upon infinite, and which is 0. So this limit will always take the value 0. So this is 0, this is 0, this is 0, this is 0. That means from here we can say value of L is simply 1 by 2. Now we'll find the value of M. Now for M, we have this limit x tends to minus infinite, and again we'll get this same differentiation. It will be 2x plus e to the power x upon x square plus e to the power x into x to the power 4 plus e to the power 2x upon 4x cube plus 2 into e to the power 2x. Now here this is x and x4, x to the power 5. Here it is x square and x cube, x to the power 5. So we'll divide everything with x to the power 5. So we can write limit x tends to minus infinite. This is 2 plus e to the power x upon x, and here it will be 1 plus e to the power 2x upon x to the power 4, and this is 1 plus e to the power x upon x square, and here will be this 4 plus 2 e to the power 2x upon x cube. Now e to the power nx upon x to the power r, where limit x tends to minus infinite, e to the power minus infinite is 0, and 0 upon infinite is 0. So all these terms, they will be 0. So from here we'll get the value of m as also 1 by 2. So L is 1 by 2 and m is also 1 by 2. In this case, answer to this question will be L equals m, and that's your option A. Now here the question is, we need to solve this limit x tends to 0 sin 6x square upon log cos 2x square minus x. Now what we'll do is, we'll write this as limit x tends to 0 sin 6x square upon 6x square, and here will be this 6x square upon log cos 2x square minus x. Now this is standard limit 1, and this is 0 upon 0 form, and for this we'll use L'Hopital's rule. So we can write this as limit x tends to 0, and there will be 12x, and here it is 1 upon cos 2x square minus x, and this is minus sine 2x square minus x into 4x minus 1, which we can write as limit x tends to 0 minus 12x upon 10 2x square minus x into 4x minus 1, which is still 0 upon 0 form. Now what we'll do is, we'll multiply and divide everything with 2x square minus x. Now this x will cancel. This is standard limit 1. So we put this limit, we'll get minus 12. This is minus 1. And here also will be this minus 1. So answer to this limit is minus 12. And that's your option B. Now here this first question is, we need to find this limit, which is limit x tends to 0 positive log sin x to the base sin x by 2. Now we'll write this as limit x tends to 0 ln of sin x upon ln sin x by 2, which is log 0 upon 0, that is infinity upon infinity form. we can use L'Hopital's rule. So it will be this limit x tends to 0, and here will be this 1 upon sin x into cos x, and this one is 1 upon sin x by 2 into cos x by 2 into 1 by 2. Now we can write this as limit x tends to 0, 10x by 2 upon 10x, and this is 1 by 2. We'll multiply and divide everything with x. Now this is 1, this is 1, so value of this limit is 1, and that's your option A. Now if we look at this second one, then L is this limit x tends to infinite sine under root of x plus 1 minus sine under root of x. Now we'll use the formula sin c minus sin d. So it will be this limit x tends to infinite 2 sine c minus d by 2. So it will be under root of x plus 1 minus under root x by 2 into cos under root of x plus 1 plus under root of x by 2. Now we'll rationalize this. If we rationalize this, we can write it as limit x tends to infinite, and will be 2 sine, and here will be 1 upon 2 under root of x plus 1 plus under root x, and here will be this cos under root x plus 1 plus under root x by 2. Now when x tends to infinite, this is 1 upon infinite, so it will be sin 0 is 0 into cos infinite, and cos infinite is oscillating value minus 1 to 1. Now 0 into anything finite is finite, so answer to this limit is 0. So value of L is 0. Now what about if we take this limit as x tends to minus infinite? Now if x is negative, then in that case under root x will not be defined. So answer to this question will be L is 0 and M is undefined, and that's your option B. Now here the question is, we need to solve this limit, which is limit x tends to infinite. Now we'll rearrange this a bit. So we'll write this as 2 to the power x to the power n upon e to the power x minus 3 to the power x to the power n upon e to the power x upon x to the power n upon e to the power x. Now what we'll do is we'll let x to the power n upon e to the power x as h. Now when x tends to infinite, x to the power n upon e to the power x will be infinity upon infinity form. Now if we differentiate this n times, there will be factorial n upon e to the power x, and there will be factorial n upon infinite, which is 0. So when x tends to infinite, this h, it tends to 0. So it will be this limit h tends to 0, 2 to the power h minus 3 to the power h upon h. Now this is 0 upon 0 form. Now if we use L'Hopital's rule, then we can write limit h tends to 0. This is 2 to the power h log 2 minus 3 to the power h log 3 upon 1. And if we put this limit h tends to 0, this is log 2 by 3, and that's your option B. Now here the question is, we need to find this limit, which is limit x tends to 0 positive, limit n tends to infinite, and then this summation r square into sine x to the power x greatest in a function where r varies from 1 to n whole divided by n cube. Now we can write greatest in a function of x as x minus fractional part of x. So it will be this limit x tends to 0 positive, and it will be this limit n tends to infinite, and then we can write this as summation r varies from 1 to n r square sine x to the power x upon n cube minus this limit n tends to infinite fractional part of r square sine x to the power x upon n cube. Now we know that any fractional part function, it will lie between 0 and 1. So therefore this summation r square sin x to the power x, it will always be greater than equal to 0, but it will be less than n. Now we divide everything with n cube, and if we take this limit n tends to infinite, left hand side is 0, right hand side is 0, then from sandwich theorem we can say that the value of this limit will be 0. So in that case, this limit will be limit x tends to 0 positive, limit n tends to infinite, and this is sin x to the power x, and then summation r square, and summation r square is n plus 1 2n plus 1 divided by 6. Now this is infinite limit. Now highest power of n in the numerator is 3 and highest power of n in the denominator is also 3. So answer to this limit will be coefficient of n cube in the numerator and denominator. So it will reduce to a limit x tends to 0 positive 2 sin x to the power x upon 6, which is 1 by 3 sin x to the power x. Now we have to solve this limit in x. So it is this limit x tends to 0 positive sin x to the power x whole divided by 3. Now this is 0 to the power 0 form. We can write this as 1 by 3 e to the power limit x tends to 0 x log sin x, or we can write this as 1 by 3 e to the power limit x tends to 0 log sin x upon 1 by x. Now this is infinity upon infinity form. Now if we use L'Hopital's rule, we can write this as 1 by 3 e to the power limit x tends to 0, and this is 1 upon sin x into cos x, and then it will be minus 1 upon x square. So this is 1 by 3 e to the power limit x tends to 0 minus this is x upon sin x and then into x cos x. X upon sin x is 1 and x is 0. So this is e to the power 0 and e to the power 0 is 1. So answer to this limit is 1 by 3. Now here the question is, we need to find this limit when x tends to 0. So this is L and L be this limit x tends to 0 sin x to the power 1 by x and plus this limit x tends to 0 1 by x to the power sin x. Now this is 0 to the power infinite form and this is infinity to the power 0 form. Now basically 0 to the power infinite is not an indeterminate form. So we'll actually write this as e to the power limit x tends to 0 log sin x upon x and plus this limit x tends to 0 e to the power limit x tends to 0 sin x, and this is log 1 by x. Now first we'll check its form. So this is log 0 is minus infinite and minus infinite upon 0 is actually minus infinite. So this is e to the power minus infinite and e to the power minus infinite is 0. So value of this first limit is 0. That means this L is simply the second limit, which is limit x tends to 0, and this is e to the power limit x tends to 0. We'll write this as minus log x upon cosec x, which is infinity upon infinity form. Now we use L'Hopital's rule, so it will be this e to the power limit x tends to 0, and this is minus 1 by x, and this is minus cosec x into cot x. Minus and minus will cancel, so it will be this e to the power limit x tends to 0 sin x into tan x upon x. Sin x upon x is 1 and tan x is 0, so it will be this e to the power 0. That means value of this limit is simply 1, and that's your option C. Now here the questions, we need to solve this limit, which is limit x tends to infinite. This is log x to the power n, which is n log x minus greatest is a function of x upon greatest is a function of x. Suppose this is limit L. Now this L is limit x tends to infinite. We write this as n log x upon greater function of x minus 1. Now we know that we can write greatest in a function of x as limit x tends to infinite, and it will be n log x, and this is x minus fraction part of x minus 1, or we'll write this as limit x tends to infinite n log x upon x divided by 1 minus fraction part of x upon x minus 1. Now we'll solve these two limits. Limit x tends to infinite log x upon x, which is infinity upon infinity form. Now we use L'Hopital's rule. It will be this limit x tends to infinite, and this is 1 by x upon 1, which is 0. So this limit in the numerator will be 0, and we'll solve the second limit, which is limit x tends to infinite fraction part of x upon x. Now we know that fractional part of x will always lie between 0 and 1, and we divide it with x, so it will be this fraction part of x upon x less than 1 by x. Now we take this limit x tends to infinite, it will be this 0, and then limit x tends to infinite fraction part of x upon x, and it will be 0. Then from sandwich theorem we can say that the value of this limit will also be 0. So answer to this limit is 0 minus 1, which is simply minus 1, and that's your option A. Now here this first question is, if limit x tends to 0 log cot pi by 4 minus beta x upon tan alpha x equals 1, find the value of alpha upon beta. Now we put x as 0, this is log 1 0, tan 0 0, which is 0 upon 0 form. So we'll use L'Hopital's rule, so it will be this limit x tends to 0. Now log is 1 upon x, and 1 upon x is 10, so it will be this 10 pi by 4 minus beta x, and then derivative of cot is minus cosec square pi by 4 minus beta x, and then into minus beta upon, now derivative of 10 is secant square, so it will be secant square alpha x into alpha, and this is equal to 1. Now we'll put x as 0. Now 10 pi by 4 is 1. Now cosec pi by 4 is root 2, so it will be this minus 2, and then minus beta upon alpha equals 1. So value of alpha upon beta will be 2. So answer to this question is 2. Now here the questions we are given this function gx, which is x minus 1 to the power n upon log cos to the power m x minus 1 when x lies between 0 and 2. where m and n are integers and m is equal to 0 and n is greater than 0. Now p is left-hand derivative of x minus 1 at x equals 1. Now if we look at this function x minus 1, it will be minus x plus 1 when x is less than 1, and it will be x minus 1 when x is greater than or equal to 1. So if we look at its left-hand derivative f dash 1 negative, it will be simply minus 1. So that means value of p is minus 1. Now it says limit x tends to 1 positive gx is p. So this limit x tends to 1 positive x minus 1 to the power n, and here we'll take this power out, so it will be m log cos x minus 1, and this is equal to minus 1. Now this is 0 upon 0 form. We'll use L'Hopital's rule, so it will be this limit x tends to 1 positive, and this is n x minus 1 to the power n minus 1, and this is m, and this is 1 upon cos, and cos is minus sign, so it will be minus 10 x minus 1, and this is equal to minus 1. Now this minus and minus will cancel. We can write this as limit x tends to 1 positive n x minus 1 to the power n minus 1 upon m 10 x minus 1. Now this limit, it must be equal to 1. Now we know that 10x upon x, it is 1. That means this x minus 1 to the power n minus 1, it should be actually x minus 1 to the power 1. So that means value of n is 2. If value of n is 2, this limit is 1. From here we get n equals m, and since n is 2, therefore m is also 2. So answer to this question is this option C, n equals to n, m equals 2.
Now question number 1 is, for any polynomial pt, the limit t tends to infinite pt upon e to the power t is independent of polynomial p. Justify the statement and find the value of this limit. So we have this limit, which is limit t tends to infinite p as a function of t upon e to the power t. Now if we put t as infinite, this numerator will be plus or minus infinite, and then e to the power infinite will be infinite. So when it is infinity upon infinity form, we can use L'Hopital's rule. And if we use L'Hopital's rule, we can write this as limit t tends to infinite p dash t upon e to the power t. Then again it will be plus minus infinity upon infinity. So we can differentiate it again. We can keep using L'Hopital's rule till we differentiate this function n times, which is degree of this polynomial. And if we differentiate this polynomial up to its degree, then it will be some constant upon infinite, and any constant upon infinite is simply 0. So this statement is true, and the value of this limit is simply 0. So that's your part A. Now part B is, show that q dash 0 exists and find its value. And why is it enough to calculate the relevant limit from only one side? Now we'll find q dash 0 positive. Now q dash 0 positive will be limit h tends to 0 q 0 plus h minus q0 upon h. Now this is limit h tends to 0. Now q h positive when x is greater than 0 is simply e to the power minus 1 by h. q0 is 0, and here it will be this h. So we can write this as limit h tends to 0 1 by h, and then e to the power 1 by h. Now what we will do is we'll let 1 by h as t, then we can write this as limit t tends to infinite t upon e to the power t, which is of the form pt upon e to the power t, and we know that this limit is equal to 0. So q dash 0 positive is 0. Now we need not calculate q dash 0 negative, as this given function is an even function. So suppose we have to find the value of q minus 2 will be e to the power minus 1 by 2, and which is same as value at 2. So this given function is an even function. So we just have to calculate limit from only one side. So this q dash 0 exists and its value is simply 0. Now part C is, for any positive integer n, show that qn0 exists and find its value. Here qx is the function in part B and qn0 denote the nth derivative at x equals 0. Now what we'll do is, for this part C, we have to find nth derivative of this function at 0. Now we know that qx, it is an even function. Now if qx is even, q1x is odd, q2x is even, and continues. So we can say this q&x will be even when n is even, and will be an odd function when n is an odd function. So we can simply write qn minus x will be minus 1 to the power n q nx. Now if we look at this function, which is qx, when x is greater than 0, it is e to the power minus 1 by x. Now q1x will be e to the power minus 1 by x into 1 upon x square. Now if we find q2x will be e to the power minus 1 by x minus 2 upon x cube plus 1 upon x square e to the power minus 1 by x, and then 1 by x square, which is e to the power minus 1 by x minus 2 upon x cube plus 1 upon x to the power 4. Now we keep differentiating it. We can write qnx will be of the form e to the power minus 1 by x and then some polynomial expression of 1 by x. Now if we have to find qn0 positive, will be this limit h tends to 0 e to the power minus 1 by h p1 by h. If we let 1 upon h as t, we can write this as limit t tends to infinite pt upon e to the power t, and this we have already established in part A that this is equal to 0. So from here we can say this qn0 positive will be equal to qn0 negative and will be equal to 0. That is, this qn0 will exist and it is equal to 0. Question number 57 is, consider the sequence an and it is ea to the power 1 by n minus a to the power 1 by n upon 1 by n. Now we need to find this limit, which is limit n tends to infinite an. So we can write this as limit n tends to infinite and then ea to the power 1 upon n minus a to the power 1 upon n upon 1 by n. Now what we'll do is we'll let 1 upon n as t, then we can write this limit as limit t tends to 0 ea to the power t minus a to the power t upon t. Now this is 0 upon 0 form, so we can use L'Hopital's rule. So we can write limit t tends to 0 ea to the power t into log ea minus a to the power t into log a. Now we'll put t as 0, so we'll get this as log ea minus log a. So it'll be simply ln e, and ln e is nothing but 1. So answer to this limit is 1, which is none of the above, option number D. Now question number 58 is, let an be a sequence of real numbers satisfying mod an is less than or equal to 1 for all n. We define an as 1 by n a1 plus a2 plus an. Then For n greater than or equal to 1, we need to find this limit n tends to infinite under root n an plus 1 minus an. Now we look at this limit, we can write this as limit n tends to infinite. Now under root n, now what is an plus 1? It is nothing but it is 1 upon n plus 1 a1 plus a2 plus an plus 1 minus 1 upon n a1 plus a2 plus an. Now we'll take LCM, we can write this as limit n tends to infinite under root n. Now LCM will be n plus 1 into n, and here will be n a1, n a2 and n an plus 1. So here we'll get n plus 1. Now n a1 minus n plus 1 a1. So it will be minus a1 minus a2 and minus an. Now we know that for any an, its modulus is always less than or equal to 1. So we can say this limit is less than or equal to limit n tends to infinite under root n upon n plus 1 into n, and here we can write this as n mod an plus 1 plus mod a1 plus mod a2 plus mod an. Now maximum value of any an is 1, so we can write this is less than or equal to limit n tends to infinite, and this is under root n. Now this is n, and then maximum value for each is 1, so it will be 1 plus 1 plus 1 up to n upon n plus 1 into n. So we can write this as limit n tends to infinite under root n into 2n upon n plus 1 into n. This n will cancel. Now power in the numerator is less than power in the denominator, so that means this limit will be 0. So from here we can say that this limit, it must be equal to 0, and that's your option number A. Now the question is, we are given this function f defined from minus pi by 2 to plus pi by 2, and f0 is 1, and this integral from 0 to pi by 3 ft dt, it is 0. Now which of the following options is or are correct? Now what we'll do is, we'll assume a function gx, which is this integral from 0 to x ft dt minus sine 3t in the interval x belongs to 0 and pi by 3. Now if we find g0, it is 0 and sine 0 is also 0. So value of g0 is 0, and if we find g pi by 3, this integral from 0 to pi by 3, it is 0, and then sine pi will also be 0. So this function gx, it is continuous differentiable. g0, it is equal to g pi by 3. That means this function gx, it satisfies the condition for Rolle's theorem. Then from Rolle's theorem, we can say there exists at least one c in the interval 0 to pi by 3 such that g dash c is 0. Now if we differentiate this, then we can write this is fc minus 3 cos 3c equals 0. So this equation fx equals 3 cos 3x will have at least one solution in 0 to pi by 3. That means this option A, it is correct. Now for this option B, again we'll assume a function and let this function be hx, which is this integral from 0 to x ft dt plus cos 3t plus 6x upon pi in the interval 0 to pi by 3. Now this function again is continuous and differentiable. Now if we find h0 will be cos 0 is 1, and h pi by 3, this integral will be 0. Now cos pi is minus 1, and this value will be 2. So value of h pi by 3 is 1. So again this function hx, it satisfies all the three conditions of Rolle's theorem. So again from Rolle's theorem we can say there exists at least one c in the interval 0 to pi by 3 such that h dash c is 0. Now if we differentiate this function,
we can write FC minus 3 sine 3C plus 6 upon pi will be 0. So this equation fx minus 3 sine 3x equals minus 6 upon pi has at least one solution in 0, 3, which means this option B is also correct. Now, if we look at this option C, which is this limit x tends to 0, x into this integral from 0 to x ft dt upon 1 minus e to the power x square. Now, what we'll do is we'll multiply and divide it with x square. Now, we can rearrange this limit as limit x tends to 0, this integral from 0 to x ft dt upon, now x and x will cancel, so it will be this x into, now this is standard limit, e to the power x minus 1 upon x, it is 1, and here it is 1 minus e to the power x square, so this value will be simply minus 1. Now this is 0 upon 0 form. If we use L'Hopital's rule, we can write limit x tends to 0 fx upon 1 and this minus, which is equal to minus f0, and the value of f0 is 1. So value of this limit is minus 1, which means this option C is also correct. Now if we look at this option D, then for this option D we can write limit x tends to 0. Now this is sin x upon x and then this integral from 0 to x ft dt upon x. Now this is standard limit 1 and this is 0 upon 0 form. So again, if we use L'Hopital's rule, it will be f0 and f0 is 1. So this value is actually 1 and not minus 1. So option D is incorrect. So the correct options are A, B and C.